Hello and welcome to another exciting lecture for stats. In this lecture we will be talking about data transformations, percentiles, z-scores, and the standard normal distribution. Getting right into the learning objectives, so for data transformations, you should, by the time you watch this, know how to differentiate linear and nonlinear transformations. For percentiles, you should be able to calculate percentiles and area under the curve. We'll skip around on this throughout this lecture. Then for z-scores, you should be able to calculate and interpret z-scores. That's very important, as well as identifying the two core properties of z-scores that are also the two core properties of the standard normal distribution, which gets us to learning objective 5, which is explain the usefulness of the standard normal distribution. And you're going to find that that usefulness is very similar to something we've already talked about prior to this. So that first learning objective, being able to differentiate linear and nonlinear transformations. Well, with data transformations, there's actually two categories of data transformations, that is linear and nonlinear. Interestingly enough, I've got z-scores here as well, which is one of the major things we're going to talk about in this set of slides. Well, z-scores are a special type of linear transformation. So we will get back to that and we'll come back to that. They're a type of transformation that we use to basically standardize or normalize our data. So it's a special type of transformation, but it is a type of linear transformation. So really there's two categories here, linear and nonlinear, and you should be able to differentiate between the two. Let's get right into linear. So linear transformations, they involve basically the use of one or more constants that involve multiplication and division and or addition and subtraction. When you do a linear transformation, so an example would be like over here, this x, it's called x prime. It basically means x converted. It's the converted x value. So this column, we've got our x values. And then in this column, we've got our x primes. And essentially what you're doing is you're taking and doing this linear transformation where you're applying constants. So we're going to take our x value and we're going to multiply it by 2. So we're multiplying it by a constant. That constant's 2. And then we're adding 5 to it. So that's a constant as well. So for example, on this first one, we'd have 2 times 3 plus 5. So 11. And you do that the same way through all of them. An important component of linear transformations is that the mean and the standard deviation may change when you apply a linear transformation. However, the shape of your distribution will not change. Values that are greater than other values will remain greater than other values. The essential shape, just like we talked about last week with the shapes of distributions, skewness, kurtosis, things like that, the shape itself will not change with the linear transformation. It may, and it will, the mean and the standard deviation will likely change. So it's a shift in location is a lot of the way this is explained. It might shrink it or grow it, but the distribution, the shape of it, remains the same. So one of the main things is it's a change in location. Let me erase what I wrote here and look at example here. So the mean of the x's is 3.43. The mean of the x primes is 11.86. The standard deviation goes from 1.59 to 3.18. So those things changed. But if you looked at the shape of the distribution, how they plotted out on a graph, that would be the same, even if it might have shrunk. So a linear transformation is considered to be a change in location. So that gets us to the question, why use a linear transformation? And it's because, again, that linear transformation can shift our data from one point to another. It can change the size of it. It can change location. It just does not change the shape of the distribution. So you can take let's say you've got a reaction time, and your reaction times are extremely fast. Well, you can multiply those reaction times by 1,000, linear transformation, and your primes are now numbers that are more easily understood. The numbers, once you do that conversion, can be much easier to work with. And because we've maintained the shape of the distribution, they can still be interpreted in the same way. You can't do ratios per se, but you can do comparisons between whether one variable is how it is in comparison to another. And if you do a standard linear transformation, which is what we'll talk about later, you can even make those same assumptions, those ratio comparisons. What about the other side of the coin? That is nonlinear transformations. So nonlinear transformations not only will change the location, but it will change the shape of the distribution. So if you've got skew and kurtosis, you can do a nonlinear transformation to correct for that. You'll sometimes see this in stats where you've got extremely skewed data. There are certain types of transformations you can do, like 1 divided by x, or even log x. These are types of transformations you can do such that they will correct for that skewness. So different examples here, x squared. So you're multiplying each x by x. So you're not multiplying x by a constant, you're multiplying it by itself. 1 divided by x, so it isn't x divided by a constant, it's 1 divided by the x. Logs x times y, so you're multiplying each x times a corresponding y. These types of transformations are not linear, because again, they won't preserve the shape of the distribution. They will only, or I shouldn't even say only, they will allow you to correct for shapes of distributions that are not good or not able to be run with certain statistics. Some nonlinear transformations do preserve rank order. What that means is that the order will remain the same. The highest number will remain the highest number. The next highest number will remain the next highest. Sometimes they reverse rank order. That's what you see over here as an example. The smallest number becomes the largest number becomes the smallest number. So some do not preserve rank order. Some will even mess it up even worse than that, where rank order will just get thrown all over the place. So those that do preserve rank order are important to note, because they can then be used to correct for positive or negative skew, such as like with this one here, where you've got this really high and then it just goes off into the distance. Instead, now you've got this. It's not the greatest distribution after the correction, but it does correct enough that there is less skew in the distribution. And it still does preserve rank order in a way here. It just reverses the rank order. So you could do a reversal after that, and then you've corrected for that type of reversal. So why would we conduct a nonlinear transformation? We'd conduct it when we have skewed data, because when it preserves rank order, it can change the shape of the distribution. So the advantage is that some analyses require a normal distribution in order to run them. When we get to actual tests after we get done with probability, we will start talking about the different statistical tests. And one of the things we will talk about, we will look at, is that each and every test, every single test in statistics, every single statistical test requires certain assumptions to be met. Some of the assumptions for a lot of the tests are that the distribution is normal. And we'll explain exactly what that is in a minute, but the distribution must be normal. And since the distribution must be normal, actually we explained that in the last chapter, the distribution must be normal. If it's not, if it's highly skewed, then you can't run that specific stats test on it. You have to run a different one. If you do this nonlinear transformation, it allows you to run that test on it. Should you? That's another question entirely, because the disadvantage of a nonlinear transformation is it becomes very difficult to interpret the values of the data. You've taken data that might be interval or ratio and turned it into ordinal if the rank order is even preserved. If the rank order is not even preserved, it's not even ordinal anymore. But if the rank order is preserved, you've got ordinal data, and you can run an ordinal test on it, but you shouldn't be running even an ordinal test on, or a lot of the tests you can't run on ordinal data, you've got to run on interval or ratio data. So that kind of throws a wrench in this. Some analyses require the normal distribution. By converting it with a nonlinear transformation, what you're essentially doing is you're converting the data from interval or ratio to ordinal. So the advantage of having a normal distribution and being able to run a test, you're now breaking the assumption of having interval or ratio data. So it's really just complex, and I don't recommend doing it. The only time I've ever done a nonlinear transformation is in stats classes. I've never done one outside of a class. So now you have to ask yourself the question, is a transformation linear or nonlinear? You can actually use the equation for a line here to see if it's linear or nonlinear, with one exception. So if the transformation fits this equation in some way, shape, or form, where a and b are constants. They have to be constants. They can't be like, you can't replace b with x, so they have to be constants. And specifically, b is not 0. The transformation is linear. If b becomes 0, you're basically eliminating the x, and you're just turning all of your x's into a. So it's not a linear transformation in that way. So if b is not 0, a and b are constants, and it fits this equation in some way, well, like through manipulation you can get it, but then the transformation is linear. So looking at an example here, scores are multiplied by 10, and then 25 is added. So we plug it into the equation. It's multiplied by 10, so it's bx is 10x, and then 25 is added, so the a is 25. You notice again, it's not exactly the same. That's because you can move the a to after. You can do some division here and there, stuff like that. But a is 25. B is a constant, and it is not 0. Therefore, this is a linear transformation. So if I give you this example right here, you should be able to then say it's linear. How about another one? Scores are multiplied by 0 and 10 is added. Well, a is a constant, but b is a constant as well, but it's equal to 0. So because of that, it's not linear. In a final example, the scores are squared. B is not a constant because in a sense, it's y equals x times x. So b is not a constant. B changes with x. So therefore, it is nonlinear. Next thing we're going to talk about is the normal distribution curve. So I talked about how data is normal. It fits the bell curve. Let's look at that a little bit more and talk about it a little bit in more detail. So the normal curve is a theoretical distribution of population scores. It's going to be a distribution that basically fits specific parameters. First, it's symmetrical and it's bell-shaped. So it looks kind of like that. I'm not the greatest drawer of a bell curve. Maybe I can... A little bit better, not perfect, but it's symmetrical, meaning you cut it in half. Each side's supposed to mirror the other. It's bell-shaped. It's shaped like a bell, as you see here. And in the behavioral sciences, it's used a lot. A lot of the variables in the behavioral sciences are normally distributed. Arousal, achievement, intelligence. I could keep going on and on. So there's many things in the behavioral sciences, many variables that fall under this normal distribution. And it's important because normality of population scores is one of the assumptions in many of our inferential statistics tests. I was just talking about that a minute ago, how tests have assumptions that must be met. Well, in many of these tests, most of the tests that are considered parametric, so they are parametric. So parametric tests all have the assumption of normality. And parametric tests are the tests where you're basically using the mean as your measure of central tendency. We will later in the semester talk about non-parametric tests. And non-parametric tests are where this assumption of normality is violated and how you use the median as your measure of central tendency instead of the mean. But when you're using the mean as a measure of central tendency, you're doing a parametric test and normality is assumed. We will talk later in the semester, I believe it's after the second test, when we're doing that transition from descriptive into inferential statistics, we'll talk about how there are ways around this assumption of normal distribution. And essentially what it comes down to is if your sample size is sufficiently large, you can assume normality even if the variable itself isn't normally distributed. But that's not something you need to know right now. That's something we will come back to in the week after the second exam. One of the principles of the normal curve is what's referred to as the empirical rule. And the empirical rule is essentially the percentages of scores that fall within so many standard deviations of the mean. So in here you see the perfect bell curve here. Like I said, I can't draw it that well. So down the middle here we've got the mean. So this is the mean. Then we talked last week about standard deviations. Standard deviations are basically standardized units of dispersion. So within one standard deviation of the mean here, both above and below, 68.2% of all scores are going to fall. Within two standard deviations, 95.4% of all scores are going to fall. And within three standard deviations, 99.7% of all scores are going to fall. Now this is with a normal distribution when it's bell-shaped. If it is skewed data, these percentages are going to go down. There's actually something we're not going to talk about in this class, but it's called Chekhov's theorem, and it basically says or dictates how much percentage at least you're going to have, no matter how skewed the data, at least X amount of scores are going to be within one standard deviation. You guys don't need to know that. That's a little bit more advanced stats. For this class, you just need to know when you're talking about the normal curve, and you've got this normal distribution, a symmetrical bell-shaped curve, that 68.2% fall within one standard deviation, with 34.1% above and 34.1% below. These have commas because I took this from a European site, and in Europe they use commas instead of decimals. Then 95.4% fall within two standard deviations, and between 1 and 2 standard deviations is 13.6, and between -1 and -2 is 13.6. Again, it's symmetrical, so it's the same on both sides. Then within 3 standard deviations is 99.7% of all scores, 2.1% between 2 and 3, 2.1% between -2 and -3, and then 0.1% above 3 and 0.1% below 3. And it continues going down from there. So, practice question. Go ahead and answer this. Pause it right now and answer these two questions. And then I'll come back to it. Okay, I'm assuming you've paused it, you've answered the questions, and now we can identify them. So the first question is, what percent of scores fall between -1 and -2 standard deviations? Well, -1 is right here, -2 is right here, so the answer is 13.6%. How about what percent of scores fall between the mean, we'll use this one in blue, the mean, which is right here, and +2 standard deviations? Well, there's two ways to calculate this. First, you could take this 95.4 and divide by 2. Or you can take this 34.1 and this 13.6 and add them together. So what do we get? We get 47.7%. And again, if you take 95.4 and divide by 2, you also get 47.7. So and if I asked you anything else, like how about between -1 standard deviation and +2 standard deviations? Well, then you'd take those two that we just looked at, that 34.1 and that 13.6, but also add in another 34.1 because we're going in that case between -1 and +2. We will talk in just a minute. On the next slide, we're going to get to z-scores, but in just a little bit, we'll talk about area under the curve. And essentially, that's what I'm talking about right here. We're to learning objective 2, being able to calculate percentiles and area under the curve. Well, what we're talking about here with these percentages, we're talking about area under the curve. So let's look, and let me use purple for just a second. When we're talking about between the mean and +1 standard deviation, the area under the curve, that's this area in here, is 34.1%. So the area under the curve is 34.1%. When we get to z-scores, we'll talk about the standard normal distribution. We're talking about the normal distribution right now, but we'll talk about the standard normal distribution, and we'll talk about how there are charts out there that will give you your area under the curve for all different standard deviations away, not just like an even one standard deviation. Let's say you had 1.25 standard deviations. Well, you can't do that from this chart right here because it's only showing 1 and 2. Well, 1.25, you can go to the z-score table, which again we'll talk about in just a minute, and you'll be able to find the area under the curve between the mean and that z-score, or from that z-score and below, which also gets us to the other thing here is percentiles, and percentile ranks are going to essentially be these percentages here. So at this point right here, it's 0.1%, so it's the 0.1 percentile. This right here is 2.1% plus 0.1%, so 2.2%, so it's the 2.2 percentile. Because that's a percentile is how many scores are at and below that point, and you can get that by calculating the area under the curve at and below that point and multiplying by 100. But we'll come back to that. Let's get to the bulk of this lecture, and that is z-scores. So the learning objective here is to be able to calculate and interpret z-scores. So the purpose is going to be able to convert a raw score into a standardized score symbolizing z. So here you've got x. This is going to be the formula. We're going to give that in just a second. Here you've got the mean, and here you've got the standard deviation. So when you calculate a z-score, what you need is a raw score, a mean, and a standard deviation. The z-score is going to give the distance in deviation units from the mean expressed as standard deviation units. What do I mean by this? Well, if you take a score, let's say our x equals 10. And our mean equals 100, and our standard deviation also equals 10. Let's actually use an x score of 110, not an x score of 10. Our standard deviation is 10, our x score is 110, and our mean is 100. Well, if we plugged it into this formula, we'd get 110 minus 100 divided by 10, or 10 over 10, or 1. And what we're essentially saying is the score of 110 is one standard deviation above the mean. And if you take the mean and look at it again here, the mean is 100. If you added one standard deviation and the standard deviation is 10, you add 10 to 100, you get 110. So a x score, a raw score of 110, is one standard deviation above the mean. And that's essentially what we're doing with z-scores. We are converting a raw score into a standard deviation score unit. It's going to say how many standard deviations above or below the mean that raw score is. Let's say we had a raw score of 90, and we plug that in. Well, if you plug in 90 minus 100 divided by 10, it's negative 10 divided by 10, or negative 1. So in that case, you're saying that 90 is one standard deviation, negative 1 specifically, one standard deviation below the mean. But why is this? I mean, you can just look at 90, see it's 10, see it's 1 below, but let's say we had an x-score of, well, 106. So we're going to plug in, we've got z here, let's just do it right here. Z equals 106 minus 100 divided by 10. We get 6 over 10, or 0.6. And what we can say there is that since we get a z-score equals 0.6, that 106 is 0.6 standard deviations above the mean. If we'd gotten a negative number, it would be that many standard deviations below the mean. So a z-score then helps us put a particular individual score into perspective. If we just have the score, just 110 here, it doesn't mean anything by itself. By converting it to a z-score, we now know it's one standard deviation above the mean. So z-scores, they have the same shape as a set of raw scores from which they're transformed. They have the same shape because a z-score transformation is a linear transformation, and z-scores serve as one of our very important descriptive statistics. We are going to use z-scores throughout the rest of the semester, so knowing how to calculate this z-score right here is really important. It's really easy. You just plug in the raw score, the mean, and the standard deviation, but we are going to use z-scores through the rest of the semester. So as I said, a z-score is a relative distance from the mean. So if we took and looked at it, the two core properties of z-scores that you can get from the z-score transformation is that once you've transformed scores to z-scores, the mean is 0. If you take, let's say, our x-score equals 100, our mean equals 100, and our standard deviation equals 10. Well, if we plug that in, z equals 100 minus 100 divided by 10, we get 0 over 10, we get 0. So our mean, which the same score as the mean, this x-score was the same score as the mean is going to be 0. So that's the first important property here, that the mean of the z-scores is 0. The next important property is that the standard deviation equals 1. The standard deviation equals 1. I did that on the previous one, but let's say we've got the x equals 110, the mean equals 100, and the standard deviation equals 10. When you plug that in, z equals 110 minus 100 divided by 10, we get 1. So the standard deviation equals 1. The mean is 0 and the standard deviation is 1. These are the two important core properties of z-scores that I guarantee you I'm going to ask on an exam. Why are your z-scores useful? Well, this comes back to the exact same thing that we talked about when we converted raw frequencies into relative frequencies, because it now allows us to make comparisons between different distributions. If we've got this distribution over here, where the raw score is 100, the mean is 100, the raw score is 110, the mean is 100, and the standard deviation is 10. If I instead had a distribution where the raw score is 11, the mean is 10, and the standard deviation is 1, well, if I did z equals, and it would be, again, x minus the mean divided by the standard deviation, which equals 11 minus 10 divided by 1, which equals 1 divided by 1, which equals 1. This score right here, this 11, is the same in relation in its set of scores as 110 is in its relation in its set of scores. They are both one standard deviation above the mean. More examples. So now we had this distribution we looked at earlier. We did the transformation to. But let's look at it prior to the transformation. So here we've got, we'll take the z-score, and we've got, let's look at first, we're looking at 5, and we're looking at 2. So the third one down and the second one from the bottom. So we take, and we had the mean here, and we had the standard deviation here. So we took the mean, 5, minus 3.43, divided by 1.59, we get a z of 0.99. That means that one is almost 1 standard deviation above the mean. And if you look at it, that actually makes sense, because 1 standard deviation above the mean would be 1.59 plus the mean, 3.43, which you actually get there is 5.02. Well, 5 is just below that, so it's just slightly less than 1 standard deviation above the mean. Let's look at 2 here. 2 minus 3.43 divided by 1.59, we get a z-score of negative 0.9. If you took 1.59 away from 3.43, you get just slightly less than 2. So 1 standard deviation below the mean would be just slightly less than 2. It would be 1.9 something. Or is it 1.8 something? It actually may even be 1.8 something. So the point is with 5, we are just about 1 standard deviation above. With 2, we're just about 1 standard deviation below. But let's do something. Let's look at that data that we transformed earlier. We took this data here and did a linear transformation on it. Well, let's look at those scores from that linear transformation. First, on the previous slide, we did the third score down, which was 5. So these are the x primes. On the x's, this one was 5, and this second to bottom one was 2. So on the x primes, if we calculate the z-scores for these, 15 minus the mean here, divided by the standard deviation here, we get the exact same score. That's because we have standardized these scores. And the same with down here with this 9, we get the negative 0.9, the same thing we got with 2 from the previous slide. This was just a linear transformation, meaning it didn't change the shape of the distribution. It didn't change how scores were in relation to others. By converting them to z-scores, we are standardizing them. It doesn't matter if it's before or after linear transformation, you're going to get the same z-scores because they are the same in relative to the rest of the scores in the distribution. This gets us to our third learning objective, or the next part of our third learning objective, since we've been calculating them already. But let's look at interpreting it a little bit more. So a student scores out of 100 possible points on 3 midterm exams and 3 courses. They get an 81 in English, an 88 in math, and an 86 in biology. I ask you the question, on which exam did the student do the best? I mean, that's a pretty easy answer when you look at it. Which one did they do the best? Well, in absolute terms, math. Because on math, they got an 88, which is higher than an 86 or an 81. But just as important is relative terms. That is relative to the others who are in the class. And how would you do this? How would you figure out which one's the best in relative terms? Well, you would convert each of them to z-scores. We don't have enough information on this slide, so let's go to the next slide. We've got these now, the raw score that we had from the previous, but now we have a mean for each test and a standard deviation for each test. So go ahead and pause the slide and calculate the z-score for each of these: English, math, and biology. Hopefully you paused it and calculated those. It's a lot better for you to learn how to do these on your own and then see if you're doing it right after I explain it. But so now let's look at each of these. So let's start with this one. So z equals, and again, remember, the z-score is z equals the raw score minus the mean divided by the standard deviation. So it's 81 is the raw score, 78 is the mean, and standard deviation is 4. So it's equal to 3 over 4, or 0.75. So z here is equal to 0.75. The next one, math. So we've got z equals 88, which is the raw score, 92, which is the mean, and 5, which is the standard deviation. We get negative 4 over 5, or negative 0.80. And then finally, we've got biology, which is 86 is the raw score, 82 is the mean, 6 as the standard deviation. We get 4 over 6, or 0.67. Now, on which test did they do the best in relative terms? Well, relative terms is going to be the highest z-score, because the highest z-score is going to be the one that is the one they did best in relation to the rest of the class. Which one of these is the highest z-score? That is 0.75, because this one is negative. They actually did the worst relative to others on math, because math's the only one they did worse than the mean. They did worse than the average. In both biology and English, they did better than average. So the answer of which one they did better relative to the rest of the students in the class is English. So that leads us to the standard normal distribution. We already talked about the normal distribution. Let's talk about the standard normal distribution. And the standard normal distribution is essentially the normal distribution once the scores have been standardized, once the scores have been converted to z-scores. So the standard normal distribution is also called the z-distribution. It has that mean of 0 and that standard deviation of 1 that I talked about. Those two core properties of z-scores, they're also the core properties of the standard normal distribution, because the standard normal distribution is a z-distribution. And it's also symmetrical. So what you get is that mean in the center, and this is 1 standard deviation, 2 standard deviations, 3 standard deviations, -1 standard deviation, -2 standard deviations, and -3 standard deviations. So I'm not going to spend extra time on that, because you already should be able to understand what is going on there, because I already explained it before. Now, some important principles when we're working with z-scores that it comes down to is things that are going to help you when you are calculating area under the curve. So we've got this distribution. Well, one thing that is the case is if you take and took the entire area under the curve, all scores under the curve, the area is going to equal 1. That is because the area, 1 means all of the area. A fraction, anything less than 1, between 0 and 1, is going to be a part or a proportion or a percentage of the area under the curve. The entire area, though, is 1. So this is all 1. However, let's say we cut it in half with the mean, and the mean is always 0, as you saw from the previous one. If you took and looked at half of the distribution, so in blue here, its area is 0.5, because it is half. 0.5, proportionally, that is half. On the other side, let's draw it in green over here, that is also 0.5. You add those two 0.5s together, and you get 1. So just to be aware, when you're looking at this, one thing that's really important to remember is the total area under the curve is 1, and the area on each side of the mean is 0.5. We will actually use that for calculating things. So it's very important that you understand that. So again, like I said before, what is the usefulness of the standard normal distribution in z-scores? Because it allows us to calculate relative location, and through that, we can calculate the percent of individual scores that are at and below any given point. Let's say we had our normal distribution here, and it had a mean here, and we were interested in, let's say we had a let's go with blue. We had a score that was -2 standard deviation, so our z-score is -2, and we're interested in what their percentile rank is. What percent of individuals scored at or below that point? We can, through using the z distribution, the standard normal distribution, we can go to a chart and actually get what's in blue here. Let's say instead we were interested in what was between that score and the mean. Well, here we can either go to a chart that's specific for it and calculate it there, or we could get the amount of scores that are from the mean and below 0.5 minus the blue, we'd be left with the green. So if you took 0.5 minus the blue, you'd be left with the green. So if all you had was the blue, you could actually calculate the green because of that property of everything below the mean being 0.5. However, what if you were interested in what is, and let me use purple here, what is above this blue line? So we're interested in everything up here. The percentage score is above it. Well, what you can do here, remember that property I said, the total area is 1? Well, if you took this total area here and subtracted off the blue, so subtracted off the blue, took the blue out, you're left with the purple. So if you take 1 minus the blue area, you can get the purple area. So that's why it's important to understand that the total area is 1, half is 0.5, so half of the distribution is 0.5 on each side of the mean. And then we can, from there, we can use various different techniques to calculate the percent of people between any two given points. So let's say we were interested in, we've got -2 standard deviations and +1 standard deviation. We got that there, and we've got this here. Well, you can actually calculate the area in blue, the +1 standard deviation, and you can calculate the area in green, the -2 standard deviations, add those together, and you get the total area between those 2 points. Another thing you can do with z-scores is extrapolate and get all of the different possible things within this equation. You could get the raw score, you can get the mean, you can get the standard deviation. As long as you're given 3 of the 4 scores, you can get the 4th one. So to get a z-score, you need the raw score, the mean, and the standard deviation. However, to get a raw score here, you need the z-score, the standard deviation, and the mean. So if you've got the mean and standard deviation and you've got a z-score that you calculated from a different variable, you can actually get the raw score from that. We'll use an example of that coming up in just a minute. Let's say you have the raw score, the z-score, and the standard deviation. Well, then you can calculate the mean. And finally, if you've got the raw score, the mean, and the z-score, you can calculate the standard deviation. So all of these, you now have the formulas for all of these. For the z-score, the raw score, the mean, the standard deviation, you can get all of these as long as you have the other 3. Anytime you have 3, you can get the 4th from it. Looking at an example of that, I took the SAT, but my school wants my HCT score. Both measure the same thing, but are on different scales. That's an important thing about SATs, ACTs. The scales are probably different than what I have here now because they change those every few years. But the point is they're both testing the same thing. They're testing your general knowledge and general intelligence. The important component here is, though, that they are on different scales. So the SAT scale is a minimum of 400, a maximum of 1600, so that's its range. The important things here is that a mean is 1,000 and a standard deviation is 200. ACT, on the other hand, ranges from 1 to 36 with a mean of 21 and a standard deviation of 5. So if you were given a score on one test, a raw score on one test, you can find your equivalent score on the other test. If you were given a raw score on the ACT or the SAT, you can get the equivalent score on the other test. How would you do that? Well, first, you'd convert it to a z-score. Then, you take that z-score and plug it into the equation for the other test, and get the raw score. Let's do an example. You get a 1350 on the SAT. So Z equals 1350 because that's the raw score. The mean here was 1,000 minus 1,000. The standard deviation was 200. So we get 350 divided by 200, or 1.75. So the Z-score for this person's score on the SAT, a score of 1350 on the SAT, the Z-score is 1.75. Now, how would we figure out what the equivalent score on the ACT would be? Well, now you go back to the equation, now for raw score, but plug in the ACT scores. So X equals the Z-score we just got, which is 1.75, times the standard deviation of the ACT, which is 5, plus the mean, which is 21. So what do we get here? We get this raw score equals 8.75 plus 21, or 29.75. So the equivalent score on an ACT to a 1350 on an SAT is 29.75. And we did that through two steps. First, we converted the raw score from the first test to a Z-score. Then we used that Z-score with the second test to see what the equivalent raw score is. Let's say instead you wanted to figure out the standard deviation on a test. So John scored an 88 on his first exam where the mean was 65 and the standard deviation was 10. Assuming that his relative precision remains the same in the class, what would be the standard deviation on a second test where a mean is 74 and a raw score of 86? So let's first plug in this first test. So we've got a raw score. He scored an 88. The mean was 65 and the standard deviation was 10. So we get a 23 over 10, or a Z-score of 2.3. Now for the standard deviation, we need to plug in that Z-score with the raw score and the mean for the other test. So the raw score on the other test was 86, the mean was 74, and now the standard deviation is 2.3. We get 12 divided by 2.3. And what do we get there? 5 point something like 22. 5.22, I think it is. Might be 5.21, but I think it's 5.22. So the standard deviation on the second test is 5.22 to keep his standing the same in relation to other people. Looking at percentile ranks, and I kind of already talked about this, so I'm not going to spend a lot of time on it. Percentile ranks are going to be basically values that tell us the percentage of scores that fall at or below that point. So if we talked about let's look at the distribution, standard normal distribution, the mean, which is 0. What percentile rank is the mean? Well, that's all scores at and below that point. What did I say just a minute ago about sides of the mean? It's 0.5. So the mean would be the 50th percentile rank. And this is the same as when we calculated it last week for the median. It is the 50% point of the scores. Well, the mean is the 50th percentile. Let's say we had a score up here. Let's use blue. Up here, what would its percentile rank be? Well, if you were given the specific Z-score or raw score, and given of course, the standard deviation and the mean, then you could calculate the percentile rank for this one by calculating the area under the curve and multiplying it by 100, and you'll get the percentile rank for this particular place because it is the cumulative percentage of scores at and below that point. And as we said before, we know the standard normal distribution is here. and then we can know the percent of scores that fall within each one. But the nice thing is that there is very handy tables out there. And those very handy tables you're going to see on the next slide are what's referred to as z-tables or standard normal distribution tables. And they give you the area under the curve for each different z-score. And you'll recall here on this one that this is z equals -1. This is z equals 1, z equals 0, z equals -2, z equals -3. Where are we at? Z equals 2, z equals 3. So you've got some pretty easy z-scores here. But what about scores that aren't that easy, like a z of 1.35, something like that? Well, that gets us to what's on this table. And this is a z-score table. But it's only half of it because it's only showing negative numbers. So it's, if we looked at the distribution, it's going to be everything with negative z-scores. So it's going to be everything to the left of the mean. We'll show one later that's got to the right of the mean as well. But this specific table is only showing negative z-scores. How do you read this? Well, you look first down this and get the number before the decimal and the first number after the decimal. So, for instance, this one is -3.0. And then you look across over here and get the second place after the decimal. So if we were interested in -3.05, we would go to this one because it's -3.0 here, and then 5, -3.05. Let's say we were interested in a z-score of -1.96. That's actually an important one. -1.9, and then we come down with 6, and we get this right here, and you actually find that that is 2.5%. That's an important one. Another important one is 1.645. I know you can't get to 3 decimals, so if you did -1.6 and halfway between 4 and 5, you get 5%. In stats, 5% is a very important number. We'll come back to that later. This 2.5% here is half of 5%. When you look at it with both sides of the distribution together, you get 5%. But 5% is important, so you'll hear these z-scores of 1.96 and 1.645. You'll hear those a few different times. Let's, however, look at an example now. So we're given a raw score of 86, a mean of 87, and a standard deviation of 6. Well, we calculated out what's the z-score. We take 86 minus 87 divided by 6, we get -0.17. So we're going to start over here on the left. We're going to go down to -0.1. And then we're going to cross that over to 7. So we are going to get -0.17. And we get a percentile rank for that person of 43.25, because 43.25% of the scores fall below that number. So if we looked at it like this, I can't draw too much on here, but if we looked at it like this, we drew it on this, we've got -0.17. Well, in blue here is 43.25% of the scores. So that's their percentile rank. But there's some other things we can do. What percent of scores fall between that score and the mean? Well, if percent of scores at and below equals, or the proportion of scores, let's say proportion. Proportion of scores at and below that point is 0.4325. Well, remember what I said before about how this half here from the mean to the left is 0.5. So if you take 0.5 and subtract off what's blue, you'll be left with what's green here. If we're interested in the percentage scores that fall between the z equals -0.17 there, which is that red line, and the mean, which is the center line, you're looking for green. So if you take 0.5 and subtract blue, you're left with green. So we get 0.5 minus 0.4325, and we are left with 0.0675. So, or 6.75%. Hopefully I haven't gone down onto the next line. So 6.75% of scores fall in the green area. How about what percent of scores are lower than X? We already calculated that. That was 0.4325. That was what we did in blue, or 43.25%. And this is 43.25% of scores are there. How about the percentages of scores above X? Well, this is where you have to apply that final principle I was talking about. Let's use purple here instead of green, and we're looking for everything above X, above negative 0.17 z-score. So what we've got here, recall that the property is that the entire area under the curve is 1. So to get purple alone, we just take 1 and subtract the blue. So 1 minus 0.4325. And we are left with 0.6, what am I looking at? 0.6675? Yep. You could also add 0.5, which is what's on the right side here, 0.5 to what you got in green. So add 0.5 to 0.0675, and you get the same thing, 0.5 plus 0.0675. Yeah, this is not 5. Let me correct that there. Or that's not 6, that's 5. I should learn how to do math. But the purple up here is 0.5675, or 56.75%. And I corrected myself there because I saw that 0.5 plus 0.06 is not 0.66, it's 0.5675. So you learn how to calculate percentiles and area under the curve, which is what we just did. You should know how to do that. That's going to be a lot of your homework coming up. This right here is a z-score that has both sides. So on the left over here, we've got the ones below the mean. It's negative z-scores. Negative z-scores. Over here, we've got positive z-scores. You notice that the z's over here are positive, they're over here, they're negative. This is all looking at area at and below that point. So if we took that 1.96 that I like, 1.96, you get 97.5% of scores, or 0.975. It's symmetrical because you'll notice that negative 0.196 we had here, negative 0.196 was 0.025. You add those together and you'll get 1. So this is the standard chart that you're going to be given, though when you do part B of the exam or the homework, you'll have open book, open note, open internet, so you can find these z-tables online, but I'll also provide these for you. You've got them in your notes, stuff like that, so you can get to them. There's actually other types of z-tables out there, so be aware when you're finding z-tables what tables you're actually using. And if you're confident in using these other tables, go ahead and use them. I've explained how to use always the area at and below, so the area left of the z-score. But there are ones like this one that show the area at and above, the proportion of scores at and above that point. There are even other ones that show the proportion of scores between the z-score and the mean. So that's what this table over here is doing. So it's just something to be aware of, that there are various different versions or ways to calculate z-scores, just because they all come out the same way, or they all get to the same answer, just in different ways. I recommend you keep using the ones from the previous slide, but if you want to use this, that's perfectly fine as well. Let's just do some practice real quick. Go ahead and pause it and answer these questions, and then I will answer them myself. Hopefully you paused it and answered them. What do we want to do now? Well, we want to find the percent of scores that fall between 88 and 120. Well, what's the first thing we're going to do? We're going to convert each of these raw scores. We've got a raw score of 88 and a raw score of 120. We're going to convert each of these raw scores to z-scores. So z equals, for a raw score of 88, minus our mean up here of 100, divided by our standard deviation of 16. We are left with negative 12 divided by 16, or negative 0.75. Technically, there'd be a 0 there, but negative 0.75. How about for the other one? Z equals 120 minus 100 divided by 16. It's 120 because of this right here. The 100 is here, the 16 is here. We're left with 20 over 16, or 1.25. So a z-score of 1.25. Now, what we're going to do is we're going to find the area between each z-score and the mean. Let's start with the negative one. So we're going to look at the negative one. What this chart is showing is everything at and below that point. But we're going to have, so this is a 0, z equals negative 0.75. We are interested in green. We're interested in the area between that score and the mean. But what we're given here is what's in blue. Because you see here, it's in blue. That's what we're given. How do you calculate green? Well, to get green, you would do 0.5, because this half of the distribution is 0.5, minus blue. 0.5 minus blue. Let me even put the 0.5 in red. 0.5 minus blue. Green equals 0.5 minus blue. So the green area is going to be 0.5 minus blue. So if we want to do that, first we need to find the blue area. And we do that by going down here, finding negative, down here, negative 0.75. And we get a value of 0.2266. So blue here is 0.2266. So if we take 0.5 minus 0.2266, we are left with 0.2734. So that is green. So green here is 0.2734. That is the first of the two. That is for z equals negative 0.75. What about for z equals 1.25? Well, for this one, we're in the positive, so we're going to find 1. Over here, we're on this one. In blue, we're going to have 1.25 here. We are going to be calculating blue from this chart, because that's what the chart looks like right here. It's blue. That's the shaded reason. So we're going to find negative 1.25. So blue here is 0.8944. How are we going to get the region green here alone? Well, we can get green alone by taking blue, which we've got there, and subtracting 0.5 because, again, this half is 0.5. So if you take off everything left of the mean there, you're just left with green. So by taking 0.8944, 0.8944 and subtracting 0.5, you are left with green, which in this case is 0.3944. So green here is 0.3944. Now to calculate the area now between that left point that we had here and that right point, so the area between negative 0.75 and positive 0.125, you add the two together. So we are going to add 0.27434, add it to 0.3944. We are left with 0.6678, I believe. So that right there is all the steps. It might seem a little bit complex, but all the steps in getting to finding out the proportion of scores. Now we convert that to 66.78%. 66.78% of the scores fall in the two green areas between a z-score of, so if we even looked at this here, we put it all together, you've got a z of negative 0.75 and a z of 1.25. The total area in between them, we'll use purple here, the total area in between them is that 0.6678 or 66.78%. Let's look at another example. We're just going to, these last few are just going to be examples. Go ahead and pause it and calculate this out, but what we're calculating is what percentage of scores fall between his score and the mean, and what's his percentile rank when Frank scores 124 on an IQ test that has a mean of 100 and a standard deviation of 16. Pause it. Okay, hopefully you've now calculated it and unpaused it. So what are we going to do first? Well, first things first, we're going to get a z-score. So what percentage of scores fall between his score and the mean? Well, when we're looking at that, what are we looking at? Well, we're looking at percent of scores between his score and the mean. If we do a z-score first, z equals x, which is 124, minus the mean, which is 100, divided by 16, you get 24 divided by 16, or 1.5. His z-score is 1.5. So his z-score is to the right. And we are interested in the percent of scores that fall between his score and the mean. So we are interested in this green region right here. After doing the previous one, you should be able to identify this pretty quickly because we're going to look over here to the right at this one. But what we're going to get is the purple region here, everything at and below that point. How do we get green alone? Well, we can get green alone by taking and doing the blue, that's 0.5. So we get what we've got here, the purple, minus 0.5. So let's calculate out that purple. We get the purple area here. We find 1.50. We get 0.9322. So the entirety purple region here is 0.9332. 0.9332 is that entire purple region. But to get green alone, we're going to subtract 0.5 from that. So it is 0.9332. Let me actually move this down here. 0.9332 minus 0.5, and we are left with the green region, which is 0.43 0.332, or 43.32% of scores fall in the green region, which is between his score and the mean. What's his percentile rank? Well, we actually just calculated this. His percentile rank is all scores at and below his point. Well, that's the purple. So that is 0.9332, or 93.32% is his percentile rank. Some people believe, some statisticians believe that you can only have whole percentage ranks. So in that case, his percentage rank would be the 93rd percentile. But I allow for decimals with percentile ranks. Like I said, some mathematicians, some statisticians say percentile ranks have to be whole numbers. I allow for decimals with it. But if you put 93rd percentile or 93.32 percentile, either case, you'll get it correct. How about a few more examples? Like I said, I want to get lots of examples here so you guys have lots of opportunities to understand this. In the lecture, there will be even more examples, but we've got 3 more slides of examples, so I'm going to go through these relatively quick. Carrie scored a 92 on this IQ test with a mean of 100 and a standard deviation of 16. What is her percentile rank? Well, first off, let's get her z-score. So z equals 92 minus 100 divided by 16 equals -8 divided by 16, which equals -0.5. So we're going to find -0.5 here. -0.50. We get 0.3085. Well, that's exactly what we're looking for. We're looking for her at and below her point. So the proportion is 0.3085. The percentile rank is 30.85. I'm just going to erase that because I can't write right now. 30.85%. How about what is the area between? So this one's going to be a little bit more tricky. What's the area between a score of 124 and 132? Well, first we need z-scores for the two. 124, z equals, this is from the previous slide, so it's 1.5. What about 132? Z equals, we'll even calculate it up here at the top. Z equals 132 minus 100 divided by 16. We get 32 over 16. We get 2. 16 there, 2. So we've got a z-score of 2. So we are trying to find the area between 1.5 and 2. So we're trying to find this green area between 1.5 and 2. Well, what you can actually do is you can find the blue area, which is that entirety there, and you can find the purple area, which is all of this including the green. And if you take away the blue from the purple, you're left with green. So all we have to do is get the two areas based on this chart here, because that is showing, this is showing everything at and below that point. So let's start with the purple area, because that's the 2. The purple area with a z-score of 2 is 0.9772. The blue area, which is -1.5, is 9332. If we take away the blue area from the purple area, we are left with the green area, which is 0.0440, or 4.4% of scores fall between 1.5 and 2 standard deviations above the mean. Okay, we'll go over the rest of the examples in class. So what did we cover today? We covered data transformations, and now you should be able to differentiate linear from nonlinear transformations. We looked at percentiles. You should be able to calculate percentiles and area under the curve. We looked at z-scores. You should now be able to calculate and interpret z-scores, which are basically a z-score is the amount of standard deviations a score is from the mean. You should be able to identify the two core properties of z-scores, that the mean is 0 and the standard deviation is 1. And finally, you should be able to explain the usefulness of the standard normal distribution. Thanks. Come on back.